to write the moment about A as a function of theta, where theta can fluctuate between 0 and 180 degrees. So I'm going to go ahead and draw our given figure here. We're going to have this vertical member that has a height of h, and then it's going to transition into a semicircle right here. Remember, a semicircle is a half circle. And that semicircle is going to have a radius of r. And the end of that semicircle is going to support a point load P, okay? Now, where is the angle theta? Well, theta is right here, okay? So basically what we're saying is P, this force P, can essentially swing from being horizontal pointing to the right, and it could swing all the way over here until it's horizontal pointing to the left. So that's what we mean by theta can fluctuate from 0 to 180 degrees. Sometimes we call this the classic swing set problem because, again, this is like a force here that could swing back and forth, okay? So point A is down here at the base. So, again, we want to write the moment about point A as a function of theta. So the first thing we need to be able to recognize is theta needs to be resolved into a vertical component and a horizontal component. Now, if P swings into this quadrant over here, of course the horizontal component would then end up being pointing in this direction, right? If P has swung all the way over here, right? But that's no problem. That's no problem. Because we're keeping this in terms of theta, our trig operations will account for that change of sign, okay? So we're going to write everything as positive, and we can kind of show physically how the sine and cosine operations will account for a change in sign. Let me erase a little bit of what I drew here just to make it look a little more clean looking, okay? So let's go to solution. Let's go to solution. And so the first thing I'm going to do is I'm going to say horizontal component of P. Okay? So why don't we call that P sub x? All right? So we're going to say P sub x equals P, right, times the cosine of theta. All right? And so the great thing about this is whether theta is between 0 and 90 degrees or theta has swung between 90 and 180 degrees, this cosine of theta will account for that sign change. If you don't believe me, just test it out in your calculator. If you typed in maybe cosine of some number bigger than 90, let's just say 100, you're going to get a negative value, and that negative value, whenever cosine of theta, whenever theta is bigger than 90, that negative value is going to account for the fact that P would be somewhere over here, okay? And then its x component is somewhere right here, all right? So the sign will take care of itself. What about the vertical component of P? So here we're going to call that Py, and of course that's just going to be P times sine of theta, all right? And the vertical component of P, if you look at how this thing can swing, it's always going to be pointing in a downward kind of sense, all right? So let's go ahead and write our moment function then. We're going to say the moment about A equals, and of course it's going to be P sub x times what? Well, times the perpendicular distance between px and h. So here's px is horizontal, so the perpendicular distance is what? It's this dimension h, right? So we're going to say px times h. What about the y component, right? So the y component of P is vertical. Here it is. What's the perpendicular distance away from A? Is it h? No. Is it r? Nope. It would be 2r, right? It's this distance right here, all right? So we're going to say py times 2r, all right? Now, from here, we can substitute in our values for px and py, or the terms, that is. So we'll get ma equals p cosine theta times h plus p sine theta times 2r. And that is our function, and that's what you would box in with a straight edge.